In the previous video, we saw what happened with the derivative of a complex valued function. Let's see now what happens with vector valued functions. So in this case, we have a function f from ab to rk, and k can be any number bigger than 1, because the case k equal 1 we have already seen. In this case, to compute, here we are going to use an arrow to distinguish that the function is taking some time interval. Okay, let's say from a to b, and it's mapping it let's say it's going to k equals 3. So it's being mapped to some path in 3D. Okay, it could be the fly moving, or a bee, okay, the way it moves in space, the trajectory of the flight. Okay. All right, so here what is happening as t moves, then the point traces the curve in space. Now, what is the derivative then? So the derivative physically is going to point, it's going to have a magnitude, that is the speed, but it's also going to have a direction that is going to tell you in what direction the curve is moving in space. The way it's defined is, as usual, limit as h tends to 0, f t plus h minus f of t divided by h. Okay, and if we look at, for example, in this function, if we were to find the derivative at this point, then we would be taking the differences, right? For points closer and closer. And eventually we would find a vector that is tangent at a given point. Okay, so this is t. All right. The way the functions are defined, right? Because f of t is given by the coordinate functions. Which the coordinate functions are just real functions that tell you what is the j coordinate at a given time. Okay, once you see it like this, I think it's clear by the properties of subtraction of vectors and then the division by a number. It's clear that the derivative at t is going to be the derivative of each of the individual components. Okay, so that's how you compute it. So the function, we say it's differentiable if each of the components is the differentiable function as a real function. Again, here there are results that we have seen that will not be true, but one result that is true here is the following consequence of the mean value theorem. Well, let's call it replacement of the mean value theorem. Okay, what we are going to do, if you notice, for a function f that goes from AB to R, the mean value theorem says f of b minus f of a equals f prime of c b minus a for some c in AB, right? But what we can always do is take the absolute values here. Well, this is a little messy. Let me do it properly. I need more space. There we go. We can always take absolute values, right? Here, I don't need a parenthesis anymore. And then just replace f prime, but by the supremum of the derivative in AB. Okay, this is an estimate that is actually, this is used very often. Okay, b minus a, actually here I don't need the absolute value either because I know it's positive, okay? But many times what we need is just an estimate, not an equality, but an inequality. And we can work with the supremum, okay? Instead of knowing that there is only one c, we just need the supremum. So that is, this type of inequality is what we can get as a replacement of the mean value theorem for a function with vector values. Okay, let's say this one is continuous in AB into RK, and it's differentiable in the open interval. Okay, then there exists some x in AB such that the inequality I was saying is respected. Okay, you take f of b minus f of a, and then this in modulus is less or equal than b minus a, and you can still say this is times the modulus of f prime of x. And then let's start with the proof. So in this case, let's have an idea of what's going on. So let's say we have here our trajectory. Again, this is f of a, this is f of b. And this is somewhere in a space. Okay, let's say this is RK. And here what we are going to, just for simplicity, we are going to define C as f of b minus f of a. Okay, so let's see in the picture. Yeah, let me place, well, no, it's fine. So this over here, this is the vector z. Okay. Now, I'm taking this vector because it's what appears on the left-hand side of what I want to prove. Okay, just for simplicity. So here we are going to define a function phi of t, which is z scalar product dot product with f of t. Okay, again, here let's say Let's say I'm looking at this particular t. Well, actually, that would be f of t. So when I look at f of t as a vector, I'm looking at the vector connecting 0 with f of t. So in this product here, oops, what I'm doing is the scalar product of these two. And to do the scalar product, you need to think of the two vectors in the same with the same origin. Okay, because that's how a vector space works. Okay, then this is basically the projection of one onto the other. Okay, so so this is phi of t. So let's say it would be something like this. The projection has, you need to adjust, okay, with the modulus, but we will see about that. All right. So once you have this phi prime of t, we want to take a derivative. So the trick here is to just go ahead and take the derivative. This is z times f prime of t, okay? And this function is a function that we can apply the mean values theorem to. So phi of b minus phi of a equals phi prime of c, b minus a, c in a, b. All right. So let's write down what is what. So this is z times f of b minus z times f of a. Okay, and this part here is z times f prime of z of c times b minus a, which is a number. So this side, we can factor out the z times f of b minus f of a. And now notice what happens. The way we defined z was as the difference fb minus fa. So that's very cool because we have the modulus of z squared, which is z times z equals z times f prime of c b minus a. So this is positive, bigger or equal than 0. So nothing changes if I take the modulus on both sides. Okay. So I will do it. And on this side, I get b minus a, which is positive, so no modulus needed, no absolute value needed. And here, yes, here I need to be careful there. But notice now what happens. So we have the absolute value of a scalar product. Notice that up to now, everything I have done is an equality. So the inequality needs to come now. And when we take the absolute value of a dot product, there is, right, there is like the one inequality that we can use here, the Schwarz inequality. Not t. There we go. So this is the modulus of z times the modulus of f prime of c. Okay, and that's it, because this modulus cancels with this one, and we have, writing down what is f, we have, sorry, z, we have f of b minus f of a less or equal than b minus a times the modulus of f prime of c. And that is what we wanted to show. Notice here, I want to emphasize that we have used Svarts inequality here because also we wanted to be able to cancel with these modulus of z on the left. Okay, it's kind of asking for it when you see the two terms and you say, oh, well, okay, if I take less or equal with Svarts, then I'm able to simplify a little bit. So that's the hint that tells you that you can go that way.